Hello, Butcher. So yesterday we started heat transfer. We just need a quick recap. Uh, Butcher, suppose this is a rod material and this is placed at room temperature. Suppose at some temperature, the temperature surrounding is 20. Let's assume temperature is 20. And this rod is placed at temperature of 20 degree. All the layers of this rod will have the temperature of 20 because surrounding temperature is 20 degree. All the layers of this rod will have a temperature of 20. Okay. Now what we did, we place this rod. One corner of this rod is placed at 100 degree. And let's take this is fixed. And this corner of the rod is placed at suppose 0 degree. And this is also fixed. And from all the sides, the rod we have done it covered with some insulated material. So that heat can flow only in one dimension, in one direction, and this is the direction of the heat. So, but if you see gradually, temperature of these layers will change, right? And this temperature will change from 0 degree to 100. Okay. Let us assume this layer temperature is 0, this layer temperature become 10 degree, this is 20 degree, this layer is 30 degree, this layer become 40 degree, 50 degree, 60 degree, 70, 80, and 90, and 100. So if you see, this layer temperature is as it is 20 degree, but this side temperature, this side layer temperature increases and this side temperature layer decreases. This happens when when heat start flowing, when heat start flowing this material, that heat flow we get two states. One state we call transient state where this temperature of this layer changes. Before the temperature was 20 degree of this layer, now temperature is 90 degree. 20 degree, 80 degree, 20 degree, 70 degree. So in transient state, temperature of the layer changes. Okay. And to change the temperature, this material absorbs the energy. This material also absorbs the energy. So you are inflowing, like suppose some energy is going from this side. Some energy might be, let's take 100 joule per second. Energy is going from the inside. So from this side, 100 joule of energy will not come. Okay. This side, it will be some less than 100 joule of energy because material is absorbing the energy. Okay. That state we call transient state. Then after this, the state reach steady state. So what happened in a steady state? Now temperature of this layer can increase up to only 90 degree. Okay. This layer temperature can increase up to 80 degree. So now temperature of this layer has reached 90 degree. This layer temperature has reached 80 degree. All the layer temperature has reached to their optimum value. Okay. Now whatever energy is coming from this side, now this material will not absorb the energy. Okay. The complete energy will come out from this part, like 100 joule per second. So this state we call transient state, and in last class we have done discussion about this. Okay. Now let's see the second step. Next step, temperature gradient. What this temperature gradient is? Its definition is rate of change of temperature with respect to the position. What is the meaning of this? So this is the rod. This corner of the rod is temperature high, and this side temperature is low. So heat is flowing in this direction. But we take direction of heat energy flow as positive direction. So suppose This direction is positive. This is x equals to 0. Okay. And this side x is increasing because in the direction of heat current, heat flow, we take it positive. Okay. But so as we are moving from this direction to this direction, temperature is decreasing, right? Because heat flowing from high temperature to low temperature. So let's see, this layer has a temperature T and the next layer has a temperature T plus B. As you know, the next layer will have less temperature. So this dT is negative. Okay? And suppose this width of this layer is dx, then temperature gradient is defined as dT by dx. This is by defined temperature gradient. So temperature gradient dT by dx, we call this term temperature gradient. So as you know, x is increasing, right? In this direction, x is increasing, temperature is decreasing. So dT by dx, this should be negative. Okay? Temperature gradient is negative. And you can say unit of temperature gradient as Kelvin for heat. Temperature by distance, right? So this is CG, sorry, SI unit of the temperature gradient. Let's see the next definition. Next definition is the heat current. So to heat current, how we define heat current? Definition of heat current. Suppose this side it is high temperature and this side it is low temperature. Heat current is defined as rate of heat flow, rate of heat. We call this rate of heat flow. We call this heat current. Or you can say rate of energy flow, heat energy flow per second. Or you can say energy flow, heat energy flow per second. Heat energy flow per second is called heat current. Generally, we indicate it like H. So heat current is I equals to, suppose in a time t, suppose from here to this side there is a flow of energy and Q energy flow in a time t. In a time t, the flow of energy is Q. So energy flow, heat energy flow per unit time is called heat current. This becomes Q by T. This is the heat current. So to heat current, you can assume heat current is same as the electric current. How you define electric current? You define electric current as flow of charge per second, right? Flow of charge per second, right? This is your heat current. So, sorry, this is your electric current. And heat current is flow of energy per second. But your heat current unit of the heat current becomes for the SI. And we are studying this topic in steady state. Okay, in steady state, suppose we have this material, this kind of material is there. And as we are talking in steady state, there is no accumulation of energy. Why there is no accumulation of energy? Because if energy will accumulate, the temperature start rising. So whatever the inflow of the energy per second, that should be the outflow of the energy per second. Else, if inflow and outflow is not equal, that means energy is going somewhere in the material, the temperature will rise. But you know, in steady state, there is no rise in the temperature. So suppose, from this end, heat current is H. And from this current, heat current is coming out is H2. So, as you know, heat current, inflow of the heat current should be equals to outflow of the heat current. So H1 should be equals to H2. But in any cross section, right? From this cross section, this heat current, just as the current flow from the cross section, similarly heat current also flow from the cross section. Suppose from this cross section, heat current is I3, then H1 H3, H1 equals to H2 equals to H3. Okay, because there should be no accumulation of energy inside the material because in steady state temperature cannot rise. Now let's see Fourier law of heat conduction. What this law says, suppose this is a conducting material, this is a material. This end of the material is at high temperature, this end is at the low temperature. And I want to write down how much the heat current flow in this material. Okay. So as you know, heat current from this section flow from high temperature to low temperature. Okay. So heat current from this cross section will be same as heat current from this cross section. So I want to write down heat current in any cross section. So suppose I want to write down the heat current in this cross section. Suppose temperature here is T and here is temperature T plus DT. As you know, DT is okay. And thickness of this material, this part is dx. So, but in this small numerature, in this cross section of a small width dx, जो heat current formula होगा, heat current formula H is directly proportional to होगा बच्चों A. A is what? A is the area of cross section. A is area of cross section perpendicular to heat flow. Same like electric current. Heat current is directly proportional to dT by dx. dT by dx is a temperature gradient across that length. Okay. As you know, dT by dx is negative, there should be one minus sign. Now we combine these two, it becomes heat current H as we combine these two laws, this heat current becomes H equals to minus Ka dT by dx. So heat current in this cross section, which has a cross sectional area A, and width of this section is dx, and dx is in the direction of current. Dx, this is in the direction of current. Remember this, the direction of current. So the formula for this cross section is this is the heat current in this cross section, where K is the proportionality constant, and proportionality constant K is called coefficient of thermal conductivity. Let's talk about K. What K is? K is called coefficient of thermal conductivity. Sometimes they ask about unit of K and dimension of K. That you can calculate. See, unit of H. H is the heat current. H is the heat current which says energy per second. So unit of H is watt, right? Heat energy per joule per second, right? And unit of K is, this is area square. So this is area per meter square, right? Temperature is Kelvin per meter, right? This is temperature Kelvin per meter. This meter square. And how much is unit of K? This K. They don't get confused. Kelvin. So this K is unit of K is what? Volt per meter. You can find out dimension also. Okay. Now one question based on K. Very simple question. Suppose you have two roads. One is made of wood. Other one is made of iron. and both these rods have same cross-sectional area. Both rods are identical. Okay, one person is holding this rod and one person is holding this rod. Suppose this side temperature is 100 degree and this side temperature is also 100 degree. So which person will feel hotter first? Either iron, the person who is holding iron, the person who is holding wood. ना पहले कौन ज़्यादा गर्म फील करेगा मैं ये देख. So of course you know this iron person, the person who is holding iron, he will feel तो उसको ज़्यादा गर्म फील होगा पहले स्टार्ट. Why? Why बच्चों? Because heat current in iron is more than the wood. And the reason, what is the reason? See, if you see H equals to this, H equals to what? It is minus Ka dt by dx. What I'm telling you, see, if all other parameters are same, this K will be different. K is more for iron and K is less than for wood. And what is the reason, for K to become more in iron? See, in solid, the reason for current flow is this vibration of the atom. Okay. Apart from vibration of the atoms, these free electrons also participate in this heat current. So what happens if they have free electrons? This side free electrons, they start moving. They get, this side temperature is high, so their kinetic energy increases and their random velocity increases. This side kinetic energy, this side electron start moving towards this side, and these electrons carry this energy. Okay, these electrons carry this energy. So free electrons is more in metal than in comparison to insulator. Okay, that's why K for conductor, या metals बोलूं बच्चों, K for metals is more than K for insulators. Okay, and reason is the free electrons. Next is heat current in cylinder of uniform cross. So what we want, I want to write down the formula of heat current for a cylinder which has uniform cross section. Okay, so suppose this is our cylinder. This side temperature is high, this side temperature is low. Okay, this side, and its length is given to us L. Its area of cross section is also given to us. Its area of cross section is A, and this area of cross section is uniform. Okay, this area of cross section is uniform throughout the length. So suppose बच्चों, from this heat current, inflow of heat current is H, and as inflow of heat, outflow of the heat current should be H. And from any cross section, the heat current should be H only, right? Because whatever current is entering from this, the same current must leave this cross section, else the energy will store and temperature start rising. Now I want to write down the formula. First we will write down the differential element formula. So first what we will see, we will have a small length cross section across the direction, in the direction of current. So let us have this direction. This is x equals to 0. Okay, and this is x-axis. And suppose this small length cylinder, has a length dx. For this small length cylinder, I can write down the heat current H equals to minus K. K is the thermal conductivity, coefficient of thermal conductivity of this material. K A into dt by dx. You know how we write dt by dx, right? So this layer temperature is T, and the next layer temperature is T plus D. So minus. Now I want to write down this formula in complete road. I want to create the formula for complete. So how do we create? But you should not think that in this small length current flow is S. So in total length, current flow will be something different. No, whatever be the current flow in this small cross section is a small length. The same current will flow from complete length. Okay. So what we need to do? So here h is constant. So what we need to do? Take h into dx one side and minus k a into dt other side. Let's integrate this. Minus, okay, let's integrate this. When x equals to 0, when x equals to 0 is this side, right? When x equals to 0 is this side, right? So that time this is temperature is T high, and when x equals to N is this side, the temperature is T. That's all. So left hand side we get H, and this side become L equals to, and this side is minus Ka into this side become T, and lower limit is TH, upper limit is T. So how much we are getting? H into L equals to minus Ka TL minus TH. So if you write down this formula, the formula for heat current become H equals to minus Ka. This is TL minus TH by L. The formula for heat current. But so if you see in this formula, this part is nothing but temperature gradient. This part is nothing but temperature gradient across the rod. See, if you compare this formula from this small length formula, the small length formula, this is also temperature gradient. Now, if you see temperature gradient, this is temperature gradient, this is also temperature. This is temperature gradient for a small length, and this is temperature gradient for complete form. But so if you see when, let's talk about temperature gradient a little bit here. This is a cylinder. In the cylinder, you take any part of the cylinder. I just see this formula. H in any part is constant. H is same throughout the cylinder. A is also constant. If H is constant, see H is constant, H is left hand side is constant, then right hand side should be constant. A is also constant throughout the cylinder. At everywhere across the length, A is same. K is constant. Then dt by dx must be constant. Dt by dx must be constant. Okay, must be constant. I'm talking about this uniform cross-sectional area. When uniform cross-sectional area, when cross-sectional area is uniform and k is also constant, then dt by dx become constant. If dt by dx is constant, it is nothing but rate of change of temperature with respect to length. So you can write this side temperature is T high, this side temperature is T low, and this total length is L. If I ask you temperature gradient across this complete cylinder, because it is constant, whatever is between these 2 points, temperature gradient, same temperature gradient will be between these two, between any 2 points will be same. So I calculate between this and this point, कितना बनेगा बच्चों? ये बनेगा T low minus T high divided by L. Rate of change of temperature. Upside it is change in temperature, and downside it is length. Okay, so we can write this. In all the question, this dt by dx will not be constant. It will be constant only when k and a is constant. Suppose in some numerical, area is changing across the length. Area is not constant across the length. Then dt by dx will not be constant. And we can't write, if dt by dx is not constant, then we can't write like this. Okay? So let us solve one problem based on temperature. So this is a rod which has a uniform cross section. Okay? Its length is given to me, which is 100 centimeter. This side temperature is 100 degree, and this side temperature is 20 degree. Now what they're asking us find out the temperature at this point. How much is temperature at this point? They're asking us to find out this temperature. Okay, and this point is 20 centimeters. So, but as you know, from this complete road, the current flow will be the same. So, left hand side H is constant. Okay, K is constant, A is constant. The temperature gradient must be constant. Okay, so what is temperature gradient? Rate of change of temperature with respect to position. So, how much rate of change of temperature in this part? This part you write T. This is T. T minus 100. Temperature gradient below low minus high लिखते हैं बच्चों हमेशा remember. Low minus T minus 100 divide by 20. Okay, this is T minus 100 divided by 20. This is the temperature gradient between the point A and between the point B. Now throughout the road temperature gradient is constant. Okay, so let's see point C. So this temperature gradient should be same between A and C, or B and C also should be same. Okay, you take any point between any 2 points, temperature gradient should be constant. Now let's calculate temperature gradient between point A and C. In point A and C is how much? 0. This side 0. This side minus 100. Okay, change in temperature divided by length. Length is how much? 100 centimeters. Okay, so now you can solve this. So T minus 100 by 20 is equals to how much? This side I'm getting minus 1. Okay, so I'm getting T minus 100 equals to minus 20. Okay, and T equals to 100 minus 20 equals to 80. The temperature of this part is 80. Understood? This is the use of temperature.